All right, hi everyone. Let's start. So today we'll do Arzela Ascoli. Um, yeah, let me finish up something from Tuesday. So if you have a box, so um, finishing claim 1 on Tuesday. What is it? Given a box, CR, I don't know, at 0, doesn't matter. At X naught, fine. So, yeah, you have some box. What does that mean? It's not minus R D, the dimension. So in 2D, you have X naught, and then let me put 2. And then this is R1, and this is R2. Okay. So you have a box. Then there exists a dense, we will define this, subset. I think we did this actually, it was homework 1. A dense subset S epsilon. So for every epsilon positive, there exists a dense subset as epsilon, so that CR X naught is inside the union of balls of epsilon disks center at this things. So the picture would be this. Okay, we will cover everything. Yeah, the whole thing. All right. Yeah, so I think in the book it's a bit complicated, but for example, in Q, it's quite more simple. So you can take S epsilon to be the rationals intersected with the set, or you can take you can just take dyadics, and I will just do the dyadics because it's a little bit cleaner. So what do we mean by a dyadics? So yeah, for simplicity, even though it doesn't matter, take CR to just take how do you say it? Take X naught to be 0, the origin, and take all VR to be 1. Just to make it a little bit cleaner. Okay. So we're dealing with you know, let me make it 2. So, for example, in t equal 2, you have 0, and it goes -1 to 1, and -1 to 1. Okay. Then by dyadics, we take so take n large enough so that 1/2 to the n is less than epsilon. And consider the set so let's do it one at a time. So you take -1, no, let me write differently. -2n, 2n, -2n, -1, 2n, 0, then 1/2n. Let me add one more. And then 2n, 2n. So this is a discrete set. And here you have 2n elements, 2n elements, and then one more. So this will be our S epsilon. So, okay, so this is for one coordinate, and then S epsilon, just take it's the same guy. So any questions? Sorry, what is dyadics? So this is what I define it. Is that an old question? Yeah, okay. Yeah, so here we define it. So these are the dyadics. N-scale dyadics are these guys. Is that okay, Tongfei? All right. Okay, fine. So then, sure. Okay, so then, as we did in example with 0, 1, we have that you know, -1, 1 is inside the union of balls S1, and they all have radius 1/2n. But epsilon is bigger than 1/2n, so you write epsilon here. And now repeat the same thing for all of them. So that gives you that CR 0, which is -1, 1 to the D, you know, is inside the union of A S1 cross SD, B 1/2n A, which is inside the B epsilon. Okay. All right. So that's how you generate what is called an. So S epsilon is called epsilon dense subset of C. So we're gonna need this. All right. Let's go into Arzela Ascoli. So I will give you the version that is most stated, and then I will give you the corollaries from the book. But first, the one that you see more often is suppose the family F is bounded in the soup norm. We always mean in the soup norm, and equicontinuous. Right, so a family inside C0K, where K is compact, and equicontinuous. Then any sequence, any Fn in F has converging subsequence for some F in continuous. Okay, so that's the one that's been used. So if you also assume F is closed, we get that the limit F is also in the family. Okay, so let's go over the assumptions before we do anything. One at a time. So remark, why bounded? Take what is it? Take K to be 0, 1, so you still are compact, but take F to just be the constant functions equal to N. Then any F and K goes to infinity. Okay, so that's why bounded. Why equicontinuous? See example from Tuesday. See example with from Tuesday. See example F equal to okay, let me write it. F equal this is the unit ball, but in the soup norm, and where we took where we looked at, Fn was 0, nx, 1, minus 1, yeah, and this guy was not equicontinuous. So it was not equicontinuous, and yeah, it was. We had Fn being not in the set. Anyhow, so that's why not equicontinuous. Why K compact? So take F to be 1. Let me see my example. So take K to be 0 to infinity, so it's not compact. and then take this to be your family. Okay. All right. Then, take any subsequence f and k. Okay. What do we have? So pointwise, f and kx goes to 0, clearly. But if you look at the sup norm over all x, minus 0, this is bigger than f and k, where we set x to be nk. Is that? This is 1 over 1 plus nk minus nk squared, so it's 1, which is strictly positive. So f and k does not go uniformly to 0. Okay. Where for d dimension, where each dimension, yeah. So we take the Cartesian product. Okay, so all right. Okay, so now let's go into the theorem. Proof of AA. Oh, we already showed that compact implies closed, bounded, and equicontinuous. Now we do the reverse. So assume these things. Star implies compact. Okay, so how do we do this? Start with any sequence. Start with any sequence fn in F. Want to find f and k so that they go to some f inside the family. Okay, so that's what we're going to do. We'll use what is called diagonalization arguments. All right. Okay. Again, step one. Since K is compact, it has a epsilon. It has an epsilon. So yeah, first of all, yes. So fix epsilon. As always. It has an epsilon dense subset, countable. So x1, x2, to infinity. Okay. No. So we had it to be finite. Yeah. So epsilon dense set Yes, so it was finite. So we took dyadics. Okay, good. Okay, next. Let's start the argument. So let y1. Well, let's say y1. No, yn. This notation will kill us. Let me call it like this. So the toughest problem in here is the notation. So that would be really the toughest. Okay, so first of all, what's the strategy? Before I jump in, let me say the strategy so that we don't get lost. Strategy. We will obtain a limit fx, a limit f at each x1 to xn. Okay, so we will have f and k xi going to f of xi. Okay, so we will obtain a limit on this dense set. Yeah, so that's the strategy. So first get a limit on the dense set, and then approximate to general x in k. Okay, so let me draw a quick picture. So this is k, and these are the dense guys, right? And then you obtain the limit in each one of them. Okay, that's step one. And then if I give you an arbitrary x, so arbitrary x, then we will approximate it. So this x will fall in one of these balls, and we will approximate to get the general f and kx going to f of x. So that's the strategy. All right, let's start. Is that okay with everyone? Okay, so the sequence. So we're doing step 1 for x1. The sequence yn defined as f of n x1 is bounded. So first of all, this is in the reals, and it's bounded because f is bounded, the family, right? We have sup of f in the sup norm is less than some m for all f in the family. Okay, that's good. So by Bolzano-Weierstrass, there exists yn and k going to y1 in R. Okay, so we have a limit. We have a convergent subsequence. F and k of x1 goes to some limit, y1. Okay. So in the book, they call this sequence lambda 1. So let me explain what they mean. So first you have f1, f2, and then actually let me draw a few more. F3, F4. And out of them, you pick a subsequence, let's say the evens. So this is Fn1, Fn2, And now these guys, they go to y1. Okay, so you pick a subsequence that converges. All right, I want to follow the notation in the book because you, so that you will read it. You have 2 places to read it. But I will try to add more details than in the book. Okay, so this is what he calls lambda 1. All right, now step 2, step 3. The sequence y2n defined as, let me call this, let me follow the same notation. But now n is in lambda 1 in that subset. Now you put x2. Again, by Bolzano-Weierstrass. So, okay, is that okay with everyone so far? We'll see what the consensus is. So again, by Bolzano-Weierstrass, there exists y2 and k. How do you call it? Going to y2 in R. So f of nk x2 goes to y2. Four people. I see more of you, so maybe you don't get it, or you don't pay attention. If you were stuck, let me know. I can go back. I only see 4 people. Or I only have 4 people paying attention. Okay, so let lambda 2 be this new, so let lambda 2, which is inside lambda 1, be this new sequence. You know, let me write it mk. You know, m1, m2, and so on. So again, let me do the pictures. So we started with f1, f2, f3 at x1, so on. And then let's say we took the even guys, you know, f6, and these guys converged. Okay, that was for x1. For x2, we started again with f2, x2, f4, x2, f6, x2, f8, x2, and so on. And then from here, we pick, let's say the, let me do one more, f10. Let's say we pick powers of 2. So this guy, and this guy. And we have, you know, f2, you know, times n, x2 goes to y2, right? So we're still using the same sequence. So lambda 2 here is lambda 2 here is 2n, which is inside the evens, lambda 1 equal to 2 times n. Let me change notation. Is that okay? And you can keep playing this game. So same for x3. You know, take take n to be in lambda 2, then you have, y3n defined as, n in lambda 2 of x3. And repeat this argument, by Bolzano-Weierstrass stress, there exist y3nk going to y3, and then, that just means this guy has a limit. All right. So altogether, let f of xi equal to yi. So that's the limit on that dense set. And we have, for n in the bottom guy, contained in all of them. We have that f of n, as you take the limit over this deepest subsequence, you have that the limit is xi for all I from 1 to n. Is that okay with everyone? Well, now they voted. Good. I think they come and go. Some people are here, some people go. Okay. All right. All right. Okay. So that's pretty useful. Right, that's what I want to say, right? Yeah. Okay, so let me say, what do they mean by a diagonalization? Now we need to, so what is our subsequence? How do you say this? I want to make So what is the diagonalization? I want to draw you a picture to see why is it called diagonalization. So, we have, so take n in lambda 1. You have n1, fn2, so on. This guy goes to y1, f of x1. Take n in lambda 2, so n1, x2. I want to call it something else. It's tricky. Okay, I know. I will call it G1n. Is that better? I don't know. Yeah, the notation is a mess. It's hard to work with. So let me think. I want to give you a nice notation. Okay. How about this? Yeah, I will use this. Okay. Okay. X2, F2, so this is +1, F2, n plus 3, X2, Okay, let me do one more. Fkn xk Fkn plus 1 xk then continue fk xk going to yk. All right. So here's the thing. What do they do? Yeah, let me call it like this. I know, I'm sorry. I'm trying to find a good notation. Let me try to. Anyhow, so all you do is you take. Let me do it like this. Okay, now I know. I'll do it like this. Okay, so this is n plus 2. Okay, I'll do it this way. Like that. Okay, so this is the diagonal guy. Yes. Okay, so let gn. So I want to say gn. Yeah. Let me call it gk x equal nk of x, where nk is from lambda k. All right. So yes. Okay. Are people still here? Can you go over quickly when finished proof? The limit part. I mean, the limit part, I think is clear, isn't it? So let me go over it again. Where is it? Again, so you have the full sequence, and then you take, you take the even guys. So that's, so lambda 2, lambda 1 are, let's say 2 times n. And then lambda 2, you just take powers of 2, which are also even. So these are the even. But here you take which are inside even. And you have a limit. So this guy's, I don't know what to say. Like, where is it? Yeah, so, we took, like, let's say these are even, so F2, F10, they have a limit. So let me say it here, just to, okay, I know, I'll put it here to make it clear. Yes, so since n is in lambda 1, you have that, since n is in lambda 2, which is inside lambda 1, you have that the limit as n goes to infinity, but inside lambda 2, okay, you have that this subsequence evaluated at x1 is y1. Okay, so we have two things. We have limit as n goes to lambda 2, n goes to infinity, fn x2 is y2. So you get both. Just because you took it to be a subset. Is that okay? Good. Okay, where am I? Here, good. So now let's go over diagonalization. Yeah, I drew these pictures, but let me just say what they do in the book and try to connect the two. Okay, so then it says for each, so let me redo the GK because it's a bit confusing. Okay, so you have these sequences, lambda 1. The notations are bad. I wish I had a better way. Let me call it, I have to think of something. How about this? How about I call it, okay, let me, I use the same G. It's bad. Let me call it H. Okay, so G1, 1, G1, 2, G1, 3. Okay, so these are the even guys. For example, this was 2, 4, 6, right? Example, this is not, then here's another way to work with subsequences. Now, lambda 2, take it to be G2 composed with G1. Yeah, I've seen this as well. That's another way to work with subsequences. Now, this guy, they're not just even. These are like 2 and then 2 to the 2 and then 2 to the 8. So I'm trying to give you as many ways as possible, many perspectives. So then lambda k is a gk of composed with gk minus 1, g1, 1. And let me now write all of them. G2, like that. Okay. All right, fine. Then let me change the note. Yeah. Then in the book they say take let n of m. Actually, let me follow their notation. So they're saying let n of k be the kth entry in lambda, let's say lambda k. So n1 is the first entry. In lambda 1. So n1 is equal to g1. N2 is the second entry. So N2 is equal to G2, G1, 2. And then NK is the kth entry. So nk is equal to gk composed with g1, and then you take k. All right. Are you still here? Hopefully. I know. Well, I'll try to go through this again, maybe on, we'll see if we have time. Okay, so again, the picture is G11, G12, G1, let me write it like this, G13, then F of G2, G11, F G1. I know this is complicated, but I'm just trying to write it in as many different ways as possible. So repeat this, and we get F of GK F of G1, okay, and then they take this diagonal. That's why it's called diagonalization, right? So this guy is N1, this guy is N2, this guy is NK. And we let G and K of X equal F of GK, oh, my notation, H of NK, G1K. Is that okay? I mean, this is very difficult. I don't know if I still have you. Yeah, just tell me. I mean, 1 person, 2 person, 3 person. All right, yeah. Fine. All right. It's very complicated. You guys are so smart. No, it's not about smart, but it's complicated. Are you sure? I don't know. I just feel it's very complicated. Okay, so let me finish up in the last minute. Okay, so what do we have? Fine, let's get it done. Okay, so want to show that G and K of X converges uniformly, oh, my notation, to some H in C0, K. So this is equivalent with showing that H of NK is Cauchy in the subnorm because C0K is complete. So if you show Cauchy, it means you have a limit. Okay? So if you show that it's Cauchy, then you have a limit by completeness of continuous functions over compact sets. So that's something we did a while back. Okay, so just 1 minute, I'm almost done. So H and K, X, and then, you know, H of different guy, H and M. So we have to show that this guy is less than epsilon. So fix epsilon. Want to find n epsilon so that this guy is less than epsilon for all k and m bigger than n epsilon, right? That's what it means to be Cauchy. This is Cauchy. In the subnorm. So we do this over all x, sup over x. Okay. All right, I have to rush. So this is just a 1/3 argument. So H and K of X find the guy who is close, you know, how do you say it? You know, find the guy that's close to x. So remember, these xi's are dense. So there is one that they're within, you know, epsilon. Okay. So then, yeah, add and subtract that. So h and k xi minus h of nm xi, and finally, yeah, I don't like running out of time. So you know what? I'm just gonna finish next week. Yeah, it's fine. I will just continue next week. This is important. So yeah, we continue next week. I don't want to rush this. So we're done for now. All right. Isn't lambda k already composed of the subsequent functions that converges? Isn't lambda k already composed? Let me see. Isn't lambda k am I misunderstanding? How do you say this? So okay, here's what why we need to use diagonalization. So okay, why use diagonalization? Um, um, you know, why not just use lambda k? Lambda k. The reason is, so remember, we have you fix epsilon, and then you get the. That's actually a very good question. We get the epsilon net x1 xn, right? And yes, it's true that you know, take if you take n in lambda n, the final guy, which is inside all the other ones. So if you take that, then you know you take the limit over the deepest guy. Then yes, you get a limit for all I 1 to n. So that's true. But why do we diagonalize? Yes, but n also will go. to infinity as epsilon goes to 0. So so what we're doing is we have limit, and then we have limit of lambda n. So that's really what diagonalization is. For all I from 1 to infinity. But xi is finite for every, yes, but you cannot rely, you see, you're not allowed to build a subsequence that depends on epsilon. We want the subsequence because we want the subsequence G and K to be independent of epsilon. Okay. No, they want a global subsequence. That's the point. That's why this is so powerful. It's not, how do you say it? How does this work? No, because then, I mean, then it's obvious. For every epsilon, of course you can find some G epsilon guy, but that's not what we're saying. What we're saying is you have the same functions, same functions. The functions don't change as you change epsilon. So, this is very important. That's a very good question. It really goes to the heart. So, you have one subsequence that converges to F for every epsilon. You don't have the functions changing with epsilon. It's the same thing with compactness, right? So in the reals, when we ask for convergent subsequence, x and k, it is also independent of epsilon. That's a very good question. Thank you. It really goes to the heart of what we're doing. Like, this is really the core question. Is the negation of the uniform convergence definition guarantees that there is a sequence? And yeah, that's the negation of it, exactly. Yeah, for some epsilon, yes. Yeah, Kim Yang, that was a very nice question. Thank you. Kim Yang, I wish you asked that during class. That's really the heart. Now a lot of people left. So, but okay, at least you guys got it. And it's in the recording. So I hope someone will see it. Thank you, Kim Yang. That was good. Okay. If you don't have any questions, guys, or you can open a private chat if you have some homework stuff. So if you want for homework, we can talk in private chat. Like, you can show me your homework approach or something. So otherwise, okay. All right. So see you next week.